today we're going to look at something called a periodic function. This is a classification of functions. It has a very simple definition. Function f is periodic if there exists a p where p is greater than 0. F of x plus p equals f of x for all x in the domain. Okay, that's a kind of an abstract definition. Let me note that if f of x plus p equals f of x, well, x plus p is obviously in the domain, so f of x plus p will equal f of x plus p will equal f of x. So 2p is another value like p that's true. I mention that because the book simply states that p is the period definition. Definition of p is the period of the function, but that's not quite true. The period of the function, I guess p is a period of the function. The period is the smallest such value. So, for example, f of x plus 4 equals f of x, but f of x plus 2 also equals f of x. Then the period is 2. Okay. These mathematical functions can be very useful in modeling a lot of real-world situations. Here's a few examples. The time on a clock. Every day we have 3 p.m. Period is 24 hours. The ocean tides. I have a slide on that I'll show you. Position of the Earth around the sun. What's the period of the position of the Earth around the sun? Yes?
365 days.
That would be a perfectly acceptable answer. Except in an astronomy class in which you would have to say, well, it's 365 and a quarter plus some little correction. It changes it. Most of the periodic functions we're going to look at in the real world are related to time in some way, but they don't have to be. Start here. We're going to look at some trig functions, and I
know everyone's at least a little familiar with them. This is the sine and the cosine function. They're both periodic. Your basic sine function has a period of, what, 360 degrees or pi. The same is true of the cosine. This is a good time to notice that the cosine and the sine look very similar. They just kind of look shifted. And when we get into trigonometry, we'll see why that is. The tangent function is also periodic, although it's a little different in that it's discontinuous every pi. Like there's a vertical asymptote and no value or undefined value periodically. Okay. If you deal with electronics at all, you're going to run into these guys. Square waves, triangles, waves, or sawtooth waves. These are typically outputs you'll see from some piece of electronic equipment. Who here doesn't own a computer? Oh, okay, good. So your computer has something they call the clock, or you get a 4 gigahertz or 3 gigahertz Pentium, right? So what that gigahertz is, we'll talk about. That's the gigahertz is the frequency, which is the reciprocal of the period, and you have in your computer something generating. Typically, it's a square wave like this. That's that period, and that's your clock, and that determines how fast your computer. The fastest your computer can do anything. Of course, to do anything with your computer, you have to do many things. So it can take more than one of these cycles to do something. Okay. Here's another example of a periodic function. You go out on a nice clear night in the right time of the year, you'll see the brightest looking star out there is not a star at all, it's Jupiter. If you look through binoculars, you'll see a little circle. And even through binoculars, you typically see 1 or 2 or maybe even 3 of the moons. Through a small telescope, you'll see 4 moons. And the moons are always kind of seem to be shuffling back and forth. And this image here is kind of you can think of it as a graph where the vertical axis is time. So over time, these moons are traveling around Jupiter, and they're periodic. You notice that the periods of these do not seem to mesh very well. That's the case. So another example of a use for periodic functions is modeling something real. Okay, here's something else that isn't astronomical, but it isn't orbiting planets. It's the sunspot cycle. This is a little irregular, but it's still modeled well, depending upon how you want to calculate it. The number of sunspots either has an 11-year or a 22-year cycle. Every 11 years, the magnetic field of the sun switches, so the whole cycle is 22. But if you're just watching sunspots at some point in the cycle, you get a maximum. Love touch pads. There we are. You get a peak. You see a peak over here, and then a peak over here. Some spots are kind of irregular, though. You know, there are periods where there are more of them and less, but it's not like something regular like Earth going around the sun. Okay. Another cycle here are tides. These are, who knows what tides are connected to? You know what determines the high tides and low tides?
The moon?
It's the moon, yeah. Yeah, the moon actually pulls on the oceans, and the gravity of the moon is enough to raise the water or lower the water, sometimes a few feet. Again, it's a little irregular, but you can kind of see here, it rotates, you know, from the Earth's point of view, the cycle is about 24 hours, but it's not really. The real cycle is the moon going around the Earth, which takes about 28 days. Right. And we have one more example here. Ironically, I'm going to wait for this noisy device to pass by. That's a street cleaner. They're periodic too, you know. They come like every Thursday at some hour. Anyone here have a car? You park in the city? If you do, you know that you better not have your car there. You get an $80 ticket now, I think. Okay, so sound waves are also periodic waves. Let's see, 2 minutes, 3 minutes. Oh, I don't want to wait that long. We have a better connection here. Let's see. I have a thumb drive, so give this a try. Tried this the other day, and here we go. Oh, I have a little video for you. That's nice. See if we get sound here.
Sets the air next to its ocean, alternately compressing and expanding it with each vibration. The variation of sound pressure can be detected not just with your ear, but also with a microphone connected to an oscilloscope that traces out a sine wave, showing how the sound pressure varies with time. We can also make sine waves with an electronic synthesizer. The number of vibrations per second is called the frequency. It's related to the sound or tone. For example, this tone has a frequency of 440 vibrations per second. Here's what happens if you double the frequency. The new sound, an octave higher, is called an overtone. And here's what it sounds like if you cut the frequency in half. The new sound is an octave lower. The height of the curve, up or down, depends on the loudness or intensity of the sound. The maximum height of the curve above the axis is called its amplitude. These examples show changes in amplitude for a given frequency. More complex sounds can be made by combining sine waves. For example, if you combine this tone with this overtone, The graph of the combination is obtained by adding the corresponding heights of the two sine curves.
Okay.
It sounds like this.
Video presentation for the day, I guess. Yeah, so sound waves are periodic waves. And, we got a little introduction there, some of the terminology. Okay, so let's talk a little bit about that. We have something called the amplitude that he mentioned of a function, which is defined as the maximum of f minus the minimum of f over 2. So in the case of a sine wave function like this, your max would be here, your min would be here, but this would be your amplitude. When the x-axis here is actually time, we have another name for the period. We can call this a cycle. So, a period and the cycle are really the same thing if you're talking about time. These have the units of time. And then we have something called frequency, which is kind of 1 over a cycle. So it has the units of 1 over time. We'll use the term frequency, again, whenever it's time-based. And the only thing left, like any other function, will have a range. In this example, the range, of course, is just all the values between the maximum and the minimum. A periodic function may not actually go through all values in its range. A ideal square wave would kind of look like this. This was like a voltage, would be a typical kind of situation. The voltage would change, and it actually would go through all the values very quickly, but there's no need, for a periodic function to do that. Okay, that's periodic functions. That's all there is. Any questions? We just have some terminology. We're going to see periodic functions coming up pretty quickly. As long as I don't end up on YouTube, I'm going to end up there anyway, right? What's that thing you do where you like use your camera and you broadcast something now?
Going live. Going live. Facebook Live.
My ears just aren't working.
Like Facebook Live.
Facebook Live, okay. That's not the only one though, right? You can like, go to some demonstration, right, or see some event. Okay. I know everyone has some familiarity with trigonometry. So I'm going to go through the next section a little bit quickly, but I just want to make sure everyone is on the same page. Maybe if you've had this before, just a little reminder will help bring you up to date. The next topic we're going to talk about is triangle trigonometry. This is the way it's usually introduced in high school, and we're going to go a little further than this, but we're going to go a lot further than this. But let's just start out with some definitions. We have a right triangle. That's my little symbol for a right triangle. This is kind of a standard way of looking at it. We have some angle here, theta. Anybody confused by Greek letters? We use Greek letters a lot in math. I don't know why we use any particular letter other than everyone knows pi, of course, but angles we often use theta. And a right triangle has a hypotenuse called L, we'll call H. And it has two legs, which we're going to give special names relative to the angle we're interested in. There's the O opposite and the A adjacent to the angle, opposite from the angle. And we define the sine of theta as the opposite over the hypotenuse. We define the cosine of theta as the adjacent over the hypotenuse. And we also have a tangent function, which we define as the sine of the angle over the cosine of the angle. So it becomes, the hypotenuse drops out, and it becomes the opposite over the adjacent. It's really important to remember, which of these legs of the triangle and the hypotenuse we're interested in. I did not learn this in high school. I learned this teaching in high school. There's a mnemonic that goes like this. It goes, so, ta, hoa. So, ta, hoa. You want to say that over and over a little bit until it kind of seeps in. So, ta, hoa. Why is that useful? Well, sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent. So that's a useful mnemonic to learn if you're not already pretty handy with these. You should note that to have a right triangle like this, theta has to be between 90 degrees and 0 degrees, strictly. There are no triangles with 0 degrees here, and if you have two 90-degree angles, what happens to your hypotenuse and your opposite? this up and it's 90 degrees. Like that. What do I know about those two lines here? They're parallel, yeah. Dig back to your geometry days. You may remember we had a transversal and alternate interiors. If they're equal, we have parallel lines, and vice versa. Okay. Wrong. Video part of the show is not over. That'll take a minute to come back, I guess. We'll get to the video in a minute. What kind of problems can we solve using triangle trigonometry? Well, I guess I want to just digress for a second. Does anyone recall some theorems from geometry that kind of look like this? Side, side, side. Does anyone recall what that is? What that theorem is? Yeah, it's a triangle theorem. Does anyone remember what SSS means? Yes?
Is it side, side, side?
Okay, it's called side, 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 yes. And what does side, side, side mean? Halfway there. Yes?
All the sides equal the same, so the degrees for each angle add up to 180.
Yes, everybody has it up there, but it's a little jumbled. Yeah, close. I mean, this just says if you have two triangles, and they have three congruent sides, that the triangles are congruent. Congruent really means that, you know, all the parts of the triangle are the same. They're not the same triangle, or not necessarily the same triangle, but we know all the measurements are going to be the same. There are a few more of these theorems. There's SAS, which you probably guess is side, angle, side. Angle, side, angle. And then, well, the last one doesn't have an, you know, it doesn't look the same. Anyone recall the could actually have angle, angle, side, but that's really no different from this. Anyone know why angle, angle, side, and angle, side, angle, and angle, angle, side are really no different? Yeah.
Two angles inside.
Well, that's what we call sophistry. You're using words to confuse me. No, these are really different. Angle, side, angle would be two angles and an included side. These two triangles are congruent. Angle side would be two angles and a side, but the side that I know is congruent is not between these two angles. Even so, I'm suggesting these are really the same for an important reason, which I heard earlier. I heard from I heard from Albert. He was on to something there. Oh, Albert, what were you saying about a triangle? Triangle and its angles? Is he with us?
That's not Albert.
Oh, I'm sorry. I know who you are.
Stefan.
You like them?
What?
No? Now I'm really confused. You are?
Stefan.
You're Stefan. All right. I guess I'm in trouble. We're marking you absent. How to fix that? Stefan, what did you say about a triangle and its angles?
They all add up to 180.
Yeah, they all add up to 180. So if I have two angles the same, I always have the third angle the same, right? So either of these is pretty much the same. But there's one more. There's one more, and it doesn't have three letters. And it doesn't have an A or an S in it, but it does have letters. Anyone remember? Okay. Don't know how we go on, but we do. Anyone remember what HL stands for? No. Okay, it's hypotenuse leg. Says you have a right triangle, and only a right triangle, and the hypotenuse and one of the legs are congruent. You have two congruent right triangles. Okay? My whole digression was just to get to that. Why is that? Well, if you have a right triangle, and you know two parts of that triangle, two more parts besides the right angle, you know a leg or a hypotenuse at an angle, two sides, whatever. You've determined the triangle. All triangles with those parts are congruent. So that tells us that at least in principle, if we have two pieces of this triangle, this right triangle, we should be able to find the rest. Okay, I think we're ready for our video interlude. Yeah. The music on these things gets really tedious, which is why I try and keep them really short.
Suppose we call this angle T. If we expand or contract the triangle by a scaling factor, we change the length of the sides, but we don't change the angle T, or the two internal ratios, A over C, or B over C. Now we will show that the ratio A over C is equal to the sine of T, and the ratio B over C is the cosine of T. Scale a triangle by by the particular scaling factor 1/c. This gives a triangle with a hypotenuse of length 1. Use this as the radius of a unit circle. Then t is the radian measure of this angle. This point has a vertical coordinate sine t and a horizontal coordinate cosine t. But these are just the lengths of the other two sides of the triangle. This shows that sines and cosines are ratios of lengths of sides of a right triangle. If the right triangle is oriented differently, it's easy to remember the ratios by thinking of them this way. The sine of this angle is the length of the side opposite the angle divided by the length of the hypotenuse. And the cosine of the angle is the length of the side adjacent to the angle divided by the length of the hypotenuse.
Okay, so question then is, what kind of problems can we solve with this information? Give you an example here. So I have a right triangle. Its hypotenuse is 10. And its angle is 60 degrees. I want to know the length of the other side. This is the right triangle. I'd like to know this angle, and I'd like to know this side. So let's try and piece this together. What would this angle be? Casey? 30 degrees, okay. How do you know that's 30 degrees?
Because the 60 plus 90 minus 180 is 30.
Okay. So you said 60 plus
90?
not 60 plus 90. I think you said 90, say 90 minus 60 equals 30? Is that what you said?
No,
Tell me what you said. I'll just write it down.
I said 90 plus 60, and then the sum subtracted from 180 is 30.
Oh, 180. Okay. All right. Equals 30. Okay. So some of the angles in a triangle are 180, right? So if you just sum up the 90 degree and the 60 degree angle, and you subtract it from 180, you get 30. Okay. Another way to look at it, since I always know there's a 90 degree angle here, I could just say 90 minus 60 equals 30, or 30 plus 60 equals 90. And that relationship has a special name. Anyone recall the name? Anyone remember the relationship between two angles that add up to 90? Begins with a C.
Complementary?
Complementary. Okay, who said that? Very good, Sophie. Since you got that one, don't answer the next one, because I suspect you know. What do we call two angles that add up to 180 degrees?
Supplementary.
Supplementary. Thank you, Henrietta. Supplementary. Okay. All right, so great, we know the angle. Does anyone recall anything about, there's something special about a 60-degree right triangle. Anyone recall something about the sides? Here's a question for you. Raise your hand if you didn't take the SATs. Really? Oh, okay. It's not required anymore. Interesting. Well, you take the SATs, you take the math SATs, you really want to know this, but it's too late for you guys. So in a right triangle that's a 60, 30, 90 right triangle, the hypotenuse has a ratio to the shorter leg. Does anyone know what that is? Yes?
2
Yeah.
6 times the bottom.
Yeah, it's half. Yeah, it's 5. We'll get to the third leg in a second, but this is so straightforward, I think you should know this. Okay, if I have a triangle where all 3 sides are the same, that is called equilateral. Equilateral. If all 3 sides are the same, what do I know about all 3 angles? They're all the same. And if all 3 angles are the same, their measure is 60. Okay. That's all, should be straightforward. Here's how you take the next step. You take the apex here and you drop perpendicular. That's a line from a point to another line that makes a right angle. That perpendicular, what does it do? It breaks it up into 2 congruent triangles. Each of the congruent triangles, like this angle is 30 degrees. So these are 30, 60, 90 degrees. Each of these, what do you know, is half of the side because we started with an equilateral triangle. So that'll get you from a 30, 60, 90 triangle from the hypotenuse to this short leg. The last leg we have to do a little work. We need to use Pythagorean theorem. All right, so this will be the square root of 10 squared minus the square root of 5 squared, or 100 minus 25, or 75, which is 5 times the square root of 3. Did I get that right? So if you multiply the short leg by square root of 3, you get the second leg. All right. Well, this tells us something, a little nice information about our trig functions. It tells us that the sine of 60 degrees is what? Well, it's the opposite over the hypotenuse. Square root of 5 over 5 square root of 3 over 10 is what? Square root of 3 over 2. Cosine 60 degrees is going to be the adjacent over the hypotenuse. It's going to be 1/2. Now, unfortunately, our brains are too small and we can't memorize every possible ratio. That's why we have calculators. Right? outdated, TI-82. But, okay, right down here we see we have a sine button and a cosine button. Does anyone recognize this window here I've gotten into? Anyone know how you get there? You may have a different kind of calculator that works a little different. Yeah. Yeah, that's the mode button. And take a look here. You'll notice the mode has this option called radian or degree. Right now it's chosen radian. I bring this up because one of the most common mistakes I run into with students is they're using their calculator to do trigonometry and it's not in the mode they thought. So always check. Right now we're talking about degrees, we're talking about 60 degrees, so we want to be in degree mode. But again, you can then, once you're in the right mode, get out by saying second quit, and then you can hit your sine or cosine button, and you can find out what your sines and cosines are. Let me add the tangent here, right? The sine over the cosine, so that's going to be just going to be square root 3. There are certain sines and cosines you should know the exact value for. You can start right here, 60 degrees. If you think about it a little, we have a complementary angle, 30 degrees. Here, sine of 30 degrees. Well, the opposite and the adjacent just switch. Down. So instead of being square root of 3 over 2, this is a half. Cosine of 30 degrees is square root of 3 over 2. And the tangent will be the reciprocal 1 over square root of 3. The reason you should know those is not because you memorize them. The reason you should know those is because you can figure out, this being an equilateral triangle, 60, 60, 60, broken in half, etc., etc. You should be able to figure that out on the fly. There's one more triangle that's like that. That should be pretty easy to remember. Figure out. That's the hopefully well-known isosceles. Is that how you spell that? Yeah. Isosceles right triangle. What are the measures of the angles for the isosceles right triangle? Okay, you tell me one and you tell me the other. You can go first.
45.
Yeah, that's one of them. Okay, Juan, what's the other one?
40.
It's 45, yeah. Right? Isosceles triangle, the opposite angles are equal. Okay. Let's assume for a second the legs are 1. How do we figure out the hypotenuse? Yeah.
Is the square root of 2?
The square root of 2, right? We can just use the Pythagorean theorem. So you ought to be able to figure this one out too. And if you can, now sine of 45 degrees is pretty simple. Somebody help me out. Opposite over the hypotenuse. 1 over the square root of 2. Cosine of 45 degrees should be even easier now. 1 over the square root of 2. And the tangent is now what? Just 1. What are you doing here? Okay. All right, let's take a more real-world kind of math problem here. What if the hypotenuse is 10 and the adjacent is 4? There's my angle. Well, I say to myself, I know the cosine of this angle. I know the cosine of theta is equal to 4 over 10 or 2/5 or whatever, 0.4. Here in my calculator, I have inverse cosine. So I can get my second inverse cosine and plug in 0.4. And I'll find out that theta is 66 degrees and 66.42182 degrees. Okay. Since we're going to run into it a little bit, I want to mention that often degrees are not listed this way, it's just a decimal. Often we'll list degrees and then minutes, we'll use a tick, and then seconds. Does anyone know the relationship between a minute of angle and a degree? So 60 minutes is equal to 1 degree. 60 seconds equals 1 minute. So I could take 0.4218 and I could convert that to minutes and seconds if I needed to. Okay, so I know this angle. We're just going to say, let's just say 66.4 for now. That tells me this angle also, right? Because they're complementary. (90 minus 66.4). 13.6. And finally, I can find the fourth side the same way I've been doing using the Pythagorean theorem, right? Square root of 100 minus 16, whatever that is. Okay, that's basic. It's basic triangle trigonometry. We just have kind of a historical footnote I want to get to here. We didn't used to have calculators, and just like I showed you, we used to have tables for logs. We used to have to do the same kind of thing for trig functions. So here's a table to five places. I don't know if you can see back there, but up in the upper left-hand corner says, I can't even read it, however many degrees. There's a different number of degrees on every page. This is a big table. So you come down, this column here would tell you minutes. And then you could read across and find sine, cosine, tangent of a function. just how we used to do it. I think that's it. That's it for today. Again, I think I'll just start posting the homework, but when we get to 3 items, that's when the homework will be completed and then you can hand it in. The next homework won't be due till next Wednesday. But again, if you see something up there, you might have